Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and I want to illustrate a uniformly most powerful test in the normal setting. The next 2 or 3 videos after this, we're going to prove theorems about uniformly most powerful tests, but I wanted to give an illustration first before I jump into those theorems. So let's let xi be normally distributed with mean mu and variance sigma squared. It's a random sample of size n. We're going to assume sigma squared is known and that mu lives in the parameter space omega, and which consists of all real numbers. We're going to do a simple versus simple hypothesis testing in the normal setting, and I do have a video out that I call simple versus simple for normal distribution. And so if you want to go back in the playlist and review that, that would be helpful. So here we're going to use the Pearson limit to construct a most powerful test for simple versus simple. So our null hypothesis is that the mean mu is some value, call it mu naught, versus some value that's bigger than mu naught. And we're going to call it mu naught plus omega, where omega is greater than 0. Now, the most powerful test, according to the Pearson limit, says that this is our test function. So phi of our data is 1 if the mean is greater than some constant, and it's 0 if it's less than some constant. So that means reject the null hypothesis. Do not reject the null hypothesis. Now C is determined by the expected value under the null hypothesis, assuming it's true. So alpha is, I said C is determined by this expected value, if I didn't say that a second ago. So mu is assumed to be mu naught in this. So alpha is equal to the expected value, and the expected value is just this probability, right? Expected value of a discrete random variable is the value times the probability of it happening, value times the probability of happening. But this is 0 and that's 1, so it's just the probability. So it's a probability that that x is greater than c. And I probably should have under the null hypothesis there. So I'll put a little mu. And then we can show, since x is a normal random variable, that the cutoff value is this, where z is greater than, z is the cutoff in the standard normal distribution that makes that tail area alpha. And so that's this. Now a lot of times you'll see it where they subtract the mean and then divide by this quantity, and that becomes a standard normal distribution, and that's greater than z alpha. But here we just moved everything over here. We're going to keep it in this fashion. And so what we do is we set this is equal to C, right? That's what goes there. Now the power is the expected value of our test function under the alternative region. So that means that the mean is really this, right? And so assuming the alternative is true, it's the probability, right? So it's still the expected value of this test function, which is this probability, but we're assuming the alternative is true. So it's the probability that our mean is greater than the cutoff value when the alternative is true. Now, notice that omega was picked generically. For any positive value, the most powerful test was this. So, since our test function, we used phi for all omega greater than 0 to construct the most powerful test. Thus, this test function is uniformly most powerful for this test here. Now, let's look at this a little deeper. So it's a uniformly most powerful for when mu is equal to mu naught versus any value greater than mu naught. It's uniformly most powerful test. And this is in the normal setting, we illustrated that. But let's look at values that are less than mu, right? So the alternative is greater than. And so let's look at values less than mu naught. Call it mu naught prime. So if we look at the probability of our test statistic being greater than the cutoff value, right? But which under the when the true mean is mu naught, this is alpha, right? Which we can subtract the mean from both sides, divide by this quantity, and that's a z random variable is greater than z alpha, right? Now we're in the standard normal setting. Now, and notice that there's no subscript here, right? Here I had to be explicit in what the mean was. But when we're in the standard normal random variable, we know that the mean is 0 and the variance is 1. But if we go from this probability to here, so instead of finding the probability that z is greater than this, let's add something to this. So it makes it harder for our random variable to be greater than it. So that means this probability gets smaller. So that's what we do from here to here. So we have the same z, we have the same z alpha, but we're going to add some positive number, right? Because mu naught prime is less than mu naught, so this is positive, positive, positive. This is a little bit bigger than this, so the probability of z being bigger than this is smaller than this probability, right? But if this right here would be the same as this probability. So if we look at this, right, this is equal to this, assuming that the true mean is mu naught prime. So if we look at this quantity, we subtract mu naught prime from both sides, and then we divide by sigma squared n, we actually get this, right? It's a standard normal, and this is the cutoff. So these two probabilities are the same. But look, this is under the assumption that for any mu naught prime, this value is less than this, which is equal to alpha. So that's telling me that the supremum for all mu such that mu is less than mu naught, so that the expected value of our test function for all mu less than mu naught, you know, it's smaller. So the biggest value is at mu naught, right? So this is what we're saying, which is alpha. So the supremum of the test function, or the level, is alpha. So this is the test function is uniformly most powerful for this test also. Now, to be quite frank, we didn't quite prove this, and this is just an illustration that if we use this test, that we can conduct a size alpha test, which appears to be most powerful. Now there's some subtleties that we'll prove in the theorem in the next video that prove it's the uniformly most powerful, but this is just a quick illustration. And one of the reasons why that we can conduct a uniformly most powerful test in this setting is because when sigma squared is known, then the normal distribution has the monotone likelihood ratio property in the test statistic x bar. That's one of the assumptions that we'll have to make to prove some theorems. And notice that's the test statistic we use for this. Okay, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.